Okay, so I want to go over a particular molecule that is very common, and you might have even seen it before, but now let's go over what it is actually structure-wise and how it relates to what we've just done today. Benzene's formula is C6H6. What makes it unusual is it's not a chain of carbons, which is what you should typically be thinking when you see multiple carbons. It forms a ring instead. So what I'm going to do is switch over to the Smart Notebook, because this is all the wording I have for this first of our 2 slides. And I'm going to draw this out for you. Knowing that it's a ring, what I'm going to do is put my carbons kind of in a ring-like manner. Remember, each carbon has 4 valence electrons. I'm not going to draw the hydrogens in yet. Hydrogens are what's referred to as terminal atoms. They end a molecule because they only have 1 electron. So really, at the end of all of this, wherever I'm short, I'm just going to have hydrogen bond to it. My suggestion with any Lewis dot that we do, ladies and gentlemen, is to single bond things early on. So I'm going to bond my carbons once each. Let's do that. And how about that? Every single carbon right now contains 2 bonds and 2 lone electrons. Since carbon had 4 lone electrons to start, it should bond 4 times to get to the octet. And I mean, I could easily tack in the hydrogens right now if I wanted to, because that could help out. But notice how every carbon's still 1 shot. What benzene is, it involves a double bond followed by a single bond, followed by a double bond, followed by a single bond. Let's get rid of this electron here and just move it here, followed by a double bond. Now this is kind of ugly because I did the mechanism of it, so if I try to pretty it up a little bit, or there's another way that this is shown. So I don't know if this next drawing will look familiar to you at all or not, but sometimes it's drawn like that. They get rid of the carbons, but they show it's a double bond, single bond, double bond, single bond, double bond. In organic chemistry, we draw things in what's called line angle format. The reason why I bring this up, and again, either drawing works just fine, is it goes back to that Pogel packet from last class. A single bond is longer than a double bond. And what we know is that in benzene, every bond between the carbons is the exact same length. It is longer than a double bond, but it's shorter than a single bond. And this is where there's limitations to Lewis dot. Lewis dot does not have a 1.5 bond. It has a single bond and a double bond and a triple bond. So what we have to do in instances where it's kind of an in-betweener is what we do is we draw the 2 options with a double arrow in between to represent it's actually a blending of the two. Then neither of these is the actual correct version, but we have to put our imagination caps on now and kind of blend the two together. And that's what my second slide is going to go over, is that blending idea of what makes it a resonance structure. Does that hexagon with the lines look familiar at all? I mean, I've also seen it drawn like this. And that's trying to represent that, hey, it's not double, single, it's just these other electrons are a little bit more delocalized, if you will. And then there's carbon chains that come off of it and all sorts of stuff as well. Okay. I don't know if you actually have to draw or write down all these statements. But what I can tell you, we use resonance to describe when there's more than one way to draw a molecule because we cannot draw it the right way. The actual molecule is a blending of the two. Two things that aren't actually accurate blended together to make something that is real. Which leads me to my analogy here, where, Tyler, I apologize if you didn't know this, unicorns are not real.
You're kidding.
I know. It's a tough day now in AP Chem. Sea serpents, like the Loch Ness Monster, not real. But if you take the two, this big sea creature and this horse with a horn, and you blend the two together, you make a narwhal. A narwhal is real. It's this thing that lives in the sea that has a huge horn on it. Resonance is taking two things that you are aware of, that you know. When you say unicorn, people know what a unicorn is. When you say Loch Ness Monster, people have an idea of what that sea serpent is. You take two things that you are aware of that are fictional. Just like my first two drawings for benzene. It's not double single bonds all the way around. It can't be, because the bond lengths are the same. But if you take those two fictional things and you blend it together, you can make something that is real. And that's how I would describe what a narwhal is. That's good stuff right there. You didn't think you were going to... Did you know what a narwhal was before this? Okay. Did everyone know what a narwhal was before this?
I didn't know they were real.
They are real, though, yeah.
Aren't they like almost like extinct?
I don't know what the use for them is evolutionary-wise anyway, so I hope that they'd be extinct soon, yeah. If you're not productive in this world, get out. I want to do one problem from that resonance worksheet with you to wrap this up. And by doing this one other problem in the resonance worksheet, I can also one more time address formal charge with you. So if you look at that resonance worksheet you picked up on the way in, I want to draw out carbonate. Carbonate is a -2 polyatomic ion. So, general rule of thumb, ladies and gentlemen, carbon goes in the middle. If it's not a carbon, whatever's the least electronegative goes in the middle. I'm going to speed up this process just a bit. I'm going to make a single bond to each oxygen right away. Now, if I single bond to oxygen, oxygen still has 1, 2, 3, 4, 5 electrons around it. So, this is my starting point. Notice that carbon is 1 electron shy of the octet. Each oxygen is 1 electron shy of the octet. What I would do in this case is I would double bond to one of these oxygens. So I'm going to erase these 2 electrons and draw my double bond. Now the oxygen's at the octet and the carbon's at the octet. when a charge is written down of -2, that means there's 2 extra electrons that are going to go into this picture. And like I tried to touch base with a few groups, some students would just be happier if I said the problem is Na2CO3, and then you have 2 sodiums that can each give an electron. But if you see it just an anion, realize there's 2 electrons available. That would go here and here. Since the top oxygen has 1 more electron than it did to start with, it has a -1 formal charge. Since the oxygen on the right has 1 more electron than it started with, it has a -1 formal charge. That's where the -2 comes from for carbonate overall. Now this is an example of resonance because I easily could have drew the double bond on the right-hand side. I could have drew it on the top. Because again, when you see something like this, it's not like carbon just picks 1 oxygen and that's where the double bond is going to stay. In actuality, all 3 of these bonds are the same length, so what I'd really have to do is draw the other 2 resonance structures to represent this as well, which is similar to the nitrate example from your textbook earlier. So again, you could finish that one on your own if you wanted to, but that's what I wanted to get to today.